значит, давайте подождем. Ну, в принципе, ладно. This is, I hope, my final part where I use some specific solution which I obtained before for PP hierarchy previously. I have shown that tau, which is as a formula y, where we have over x minus yx equals let me which is on one matrix. Well, both x's, y's, and z are n by n matrices. And we will show that our function, which is given by this formula, are solution of the whole hierarchy, and let me once again remind me that psi of x is the same. We don't have psi of x, but psi of y is psi of yt, which is trace of oh, sorry, not trace, just of yt equals from 1 to now we want to, well, let us first of all show that if V or W is equal to 0, we have just intermediate matrices like Z yx is equal to yx. When we have a very trivial solution, in this case, tau equals to x here z plus which can be written as determinant of y and determinant of x, and this is equal to okay, this is determinant 1 plus x, which does not depend on times.
Sorry, and where is psi of z?
Psi of z it becomes when we changing this psi of z becomes psi of y, and we
Okay.
okay, so let me make next and it goes on infinity I of 1 to the end over alpha times n. Yeah, I don't remember. I think we do not have dividing to the end here. We don't do this. And it is, well, we could check that this one okay, let me explain. We know that t and t times x t n gamma n infinity I gives us the same well, the same UIT, which is coefficient of t, the pseudo differential operator plus 1 minus 1 plus 2 minus 2, etc. So this solution, which differs with, with such vector, are basically the same. This is because let me call this gamma. So, as you remember, C equals tau that T, and let me call this tau let me call this whole tau is T with a dot, just and this is equal to T plus T times just function of z, and let's call it like not like dot, like dot English, and this we call regular Baker-Hayes function, and we see that what does it mean? A Baker-Hayes function is a function which is solve the system of equation at psi equals z psi when psi equals dtn psi, where bn equals to dn plus something which is a differential operator or no, no, oh, sorry, this is bt1 to the power n, etc., which is just ordinary differential operator with respect to variable t1. So here we have tn. So it is clearly that if we multiply psi by this function of z, it doesn't change anything. So psi dot of psi will also be a solution to this system. Psi dot also a solution. So we could see that these two solutions are the same. And what I want to say that if here we have these matrices are intervenient, Z and Y with the intervenient matrices X. In this case, this one be like a gauge transformation, and this will be answer which does not depend on t, so that this will give us a trivial solution that all u equals to 0. So this is basically this is a solution of the hierarchy, but this one is different. Okay, and since we know that we could factorize by this factor by factor like this, we could also rewrite our tau as, well, this will be another tau, but it will be more convenient for us to use this tau as psi y. Let me check. Psi z means y. Well, we should probably write it this way: minus times y plus 1. And this is a different tau function, but this will give us the same answer for uh, for uh, for internal solution of Kapila. Now let me start with my plan, and first first thing I want to talk about is the NPDW solution. What is NPDW? Let us recall that our KP hierarchy was it's just L, where it's a pseudo differential operator, something like a t plus 1 plus 1 plus minus 2, etc. But we know that, and we could reduce it to in NPDW if we build it L times n is differential operator. But what does it mean? That for example, n equals to 2, then the square is equal to the square plus, which is a famous PDV case. We could also choose n equals 3. This will give us a Buchinest equation, I guess. Okay. Is it clear?
Yes.
Okay. What does it mean? Let us recall that what is Bn? Bn equals to L times n plus 7. But if n equals Gn, for example, if n equals to 2, it's every even number. Then it Gn L equals Lbn in this case equals L Ln plus P. But if here we have Gn, in this case L Gn plus will give us just the same operator, and this is equals to 0. So every like for every n equals some g times n, dtn to a well, just equals to 0. This means that well, that doesn't mean that it doesn't show. Does not mean that dtn tau equals 0, but it is since as we can see, we could multiply it by this gamma factor, and it just clearly give us the same solution. This gamma factor, it just clearly give us the same solution, but it also give us a dependence on Tn. Yes, but it means that tau equals f times g, where dt1 f 0 and dtn j equals 0 for on equals to jn. Or this is this is because we don't have as I already mentioned, we could multiply tau function by something, and we obtain this factor. Sorry, maybe I did not have. Maybe this is not necessary condition, but okay, let me see. This works this way. If we have if then tau is solution of MPD. It I guess it doesn't. Okay. I don't know. Is it work another way? Is any solution of LPDB can be written this way? But I guess probably it does. And let me now check how could we modify our this solution to obtain the solution of MQU. But this is quite simple. If equals that and then is it E or A? Then I don't remember.
Where?
I'm correct, yes.
What do you ask?
Is it A or E? I don't remember.
There are two different words.
Yeah, I understand.
Then, когда, if you use A, then чем.
Okay. So then tau equals determinant of x, y, psi, z, y minus psi, y plus e is solution of MPU. Well, it is just simple calculation. Let us just t equals determinant of. Let us just remember the let us just follow the indices 1 and n. We have e1 z plus en zn e minus e2 y minus en 1 yn since this is also y to the power n, this one commutes, and we could write it this way. Equal to determinant of x e1 z e y plus e, and this will be for any indices which are the instead of n we could see t just 2 and 3 and etc. So I'm sorry. So we could see this tau function does not depend on does not depend.
Wait a minute. Sorry. You have T1Z, but you
Yes.
have minus T2Y.
Yes, yes.
Is it correct?
Yes, yes, because first of all, I had this, let me show you this formal solution. After that, I multiply this by inverse of this matrices.
Yes, you extract this to the right.
Yes, as I showed before,
Yes.
this essentially the same solution,
Okay.
but different tau functions.
Okay. But the question is why you have in one case T1, in the second case.
Oh, T1. Sorry. Yes, T1. Okay. Of course, T1. T1. I'm sorry.
Okay.
Now, Okay, it does not depend on Tn, so we have this. We have this. How to say solution. For example, if n equal to 2, then we have just let me show y equals minus z, for example, and we know that for PDV, PDV we have a tau function of PDV in the form of two matrices z plus zx equals to matrices of only one, and the PDV could be written as x with z minus z minus z minus z, and it could be written as well, similar up to Gauss transformation to the determinant of x equals 2 plus 1 plus 1, I guess, plus something like that. A solution of regular problems. Okay, now the second part of my plan is a Seleton solution. But what is Seletons? In terms of Baker-Hazer function, we define a Seleton like the following conditions. Psi, which is a Baker-Hazer function, P plus times T. Okay, I forgot that I put this in equals to is that Q of Z, where is Q of Z is a rational function. And the second condition is that we have alpha beta beta plus G beta equals to 0. E equals from 1 to n. This is an independent condition for our Baker-Hazer function. This such solution are called Seleton solution. And if
And what lambda I in this formula? So you have Q of Z in the formula for Baker-Hazer function, yes?
well, these are parameters. It's well, recall that for some
My question is that in the definition of Q, Q of Z is function of one variable.
Q, it's also a function of t, all t, but it is rational function of z, and there lambda instead of z. So it's yeah.
Lambda is what? Sorry.
Sorry, lambda is instead of z, and here we need to have different parameters here. Well, this is
okay.
okay.
So if you write down Q of T in the first formula, so replace Z and T, then
yeah.
maybe it would be better.
Yes, I guess.
Because and Z, yeah, okay. And now you just set Z equal lambda I or mu I.
Yes, let me just how could we obtain such solution from our matrix, or if we put x equals to alpha eta e minus lambda e minus mu g, lambda g minus mu y и g is delta e g mu e, z e g is delta e g lambda g. Okay, it is clear that we have zx minus yx g is equal to eta beta zeta sorry, lambda e e minus lambda g minus e z sorry, z. It's my fault. This should be z. Here we have lambda g. Here we have mu e. This is equal to alpha e divided by beta g, which is rank 1 matrix. Okay, so this is a clear our case, and let us obtain this solution t equals to determinant. Here we have c or e c minus cy, since they are both diagonal, it is c of z minus c of y, determinant of x is c z minus c y plus 1, and this will give us a sum of sum of main minors. We need to Main minus, yes.
Principal minus.
Principal, yes, yes, yes. Principal, principal minus of these matrices, and but this is a Cauchy matrix, so would be this matrices just part of that here P I guess yes this will be beyond the eta minus P mu eta and 1 over and the eta minus eta. Here we have a product of O E and these are just Cauchy matrices, and we could use a formula for Cauchy matrix determinant and obtain the following result. This will be equal to E G G G here G is some set in 1 to E less than G and E minus 1 to E minus G E minus alpha G G and E minus E. And finally, our function will be just sum over G in 1 over from 1 to n. Let us call this alpha E beta E alpha E minus mu E equals C. And this will be CI. Exponent of C and E minus C mu E, and the product of E G G E minus E plus then G and G just this multiply mu E minus mu G E minus mu G E minus mu G. This is a formula for tau function of Newton solution. Is it does somebody recognize it, or should I say some words in order to prove that this is this Newton solution as we remember them.
Okay, I have impression that this formula is a bit familiar for me.
Well, because I understood that I don't recall how to write it a tau function for certain solution, just in different way, to what expression we should compare it. But this one look like the answer, because we have here these exponents and this. Well, it looks like something with like for like 2 and 3 simple solutions. And in case just one certain solution, we just don't have here, nothing here, and just a point which should get it. Okay, now let me obtain the next part is Reginald-Snyder system. This a bit tricky, I guess, but maybe I don't know why we should in this case obtain just Reginald-Snyder, not some limit of Reginald-Snyder, but let me we have 3 matrices, like a space of space of 3 matrices X, Y, Z, satisfying the condition that Z minus Y X less than equal than 1. And let me introduce the evolution of the system. Okay. This will be something like the evolution is given by infinitely many variables, and it can be written this way: it's t y z, and it is equal to e minus c y x. Okay, we obtain some like evolution of well, I wanted to say that this in this case we have that tau equals to determinant of x t plus t, which is clearly the same as to say that the solutions it's just the same solution, but written just with another words, I guess. Because this was is it clear? Yes, that this expression will give us just another solution. I mean, the same solution as we obtained, but taking this determinant of x near c z minus c y plus 1. This is the same, but here we think of it, it's like maybe it's a little bit like this representation of operators. So we think that here matrix T it depends on infinitely many times. Yes, and we want to check how the eigenvalues of x are dependent on, let us say, T1. Is it clear?
Well, yes.
Okay. Let me just introduce the x dot is dt1 x, and it is clear that x dot is equal to v. Well, just because of definition, here we it acts here, then it acts here. If we all set, and we know that it gives us something like xz minus yx, and we know that this will be which is written here. Z dot equals to 0, z dot equals to 0. Now let us introduce the following matrix. Q is equals to U x2 minus U inverse. It is diagonal matrices of E to it. Yeah. Now let us introduce y hat, which is U y U inverse. Z hat equals to U z U inverse. V equals to U V hat V and W hat equals to W inverse. Now, with all this, after that we obtained that for now our hat equation we have Q z hat minus y hat Q equals V W hat. Yes, and well, this is the order separation, I guess. Now, Q dot equals U times x U inverse plus U V W transform U inverse plus, sorry, minus U x minus 1 U dot minus 1, and introducing m equals to U dot U minus 1, we have that U dot equals to mq plus v hat w hat transpose. Now we know that this matrix, so this matrix are diagonal. This means that and also diagonal. Okay, since this matrix is diagonal, this one this matrix is anti-diagonal because this diagonal element should be m e q e minus q e m e, which is 0. So this should have zeros on the diagonal. So this equation actually could split into two equations. First equation is that little q eta e q eta equals to v eta w eta, and the second equation, it's this one is from diagonal part, and from anti-diagonal part we see that this should be zero, so this should be zero. So we obtain from anti-diagonal part that m UG is equals VG W E minus UG. Okay, remember this one, and let us just write it. For example, another Q1 Qn dot equals dot cum inverse equals m minus well, here we use this equation for q dot and qm minus plus q z q minus y. Yes. Here we use this. Here what we do, we use this equation, and instead of VW, we replace it by this one. Okay, we obtain this equation, and now it is clear that this one are also anti-diagonal. This has zero on diagonals, and or the only thing from diagonal is here, but here we have sorry, here we have polynomials. So this will give us q dot e equals z hat minus y hat e. Now, okay, and now we will differentiate this equation once again, and we obtain QE with 2 equals to m z minus y. Y equals not equal to m like z minus y ke minus z ek minus y ek m y. And equal to okay, let me now use that this one is equal to I have no not so many time, time there, but let me just remind that this could be written from equals. Okay, we know this expression from here, and this one we could replace with k y minus y e minus half minus okay, let me just write the correct answer, and I will try to persuade you that this is answer correct. Not not okay. W E okay. Okay plus which is okay, but fine. Okay. One. What I did, I replaced m with this expression. Here I get this y minus k in denominator, and I replace this one to to this expanded with using definition of habit z and y, and but this is just the first. This is just the first term, and the second term give the same with change, just changing k to y, and plus this, well, minus the same, k replaced by y. So after like, now we remember that we have obtained here that here this one is qy dot. So we see that this d hatted w hatted with the same indices gives us qi, and we see that we have here the pair of it. So the final answer will be like sum e not equals to k q dot y q dot k y plus k minus y minus k y y k e k minus k k I that I k k minus k. This is the final expression, and now let me do some how to say assumption. First assumption is that the vector b is well equals does not have a zero component, so it could be written m, which is it is not equal to 0. In this case, we could make him just all ones, like all unities. And in this case, since we have here our here our this property, it simultaneously give us that in this case VE equals to Q dot E, and we could write it this way. Q dot I, Q dot K, Q I not K, minus Q I minus Q K, Q I dot Z K minus Q K Z Y, okay, I minus Q. And now assumption here, the second assumption is that Z K E does not equal to K equals lambda Y I K. This is a strange assumption, but well, we will see that for this assumption will give us the following thing. Because of that, we see that. Sorry, here everywhere is from this assumption, we could obtain that G hat EG equals lambda Q dot lambda E plus QG, because well, because we have that the EG hat Q plus QZ E Y EG QG equals to V EG hat. And because we have this condition, this will give us this representation. So we are we kill all dependence on Z here, and after that we could see that times E equals to 1 minus 1 square to I not equals 1. Okay, to I plus okay, to I minus okay, lambda I minus okay, lambda okay minus I. And we see here that these are equation of Original-Snyder system, trigonometric Original-Snyder system. For example, if we put lambda equals to minus 1, it gives us just well, it gives us a rational Original-Snyder system. And it was proven in our work with Zabrodin that
say it again. What corresponds to lambda equals minus 1?
I guess it's just a rational original Snyder system. And in these cases, well, in these cases, y and z from this y and z will correspond to something like q minus 1/2 L and q 1/2 L, where L is q minus 1/2 is gamma nu minus gamma nu here is gamma nu, and these are both Lex matrices of no of Resnard Snyder model, and we see that this corresponds to the case that indeed they are here instead of lambda is.
But it looks like if you put lambda b minus 1, it is not exactly the rational Rosenard-Snyder model. It's kind of degeneration.
Maybe lambda to 1, but we have took a limit, cautious limit, because here we obtain 0. And well, we know that we could changing parameters, we could obtain from trigonometric Rosenard-Snyder, we could obtain Colliger, trigonometric Colliger, rational Colliger, and rational Rosenard. So well, it's
not enough to make a limit on the invariable lambda.
Well, it's not enough. We should make a limit in variable q, I guess, also, but I think it's not a big deal how, because we show that well, in trigonometric case we obtain Rosenard, and in trigonometric case of collision model we also had proven that geometric solutions could be obtained as a also just particular case of this scheme, and as we could see this with this two probably, I would say, this one suggestion. We shall
speak about the assumption, but
assumption.
I don't agree that this assumption. You can just choose such W.
Well, no, we for example, if we have W which is not well, it has like 1 and the rest of zeros, we couldn't do this.
Of course, but I have impression that W is in your hand. No? Somebody gives you this W, or you can choose it.
Well, no, yes, I don't have.
Can you say, let us choose such W that all components are non-zero?
I don't know. I think it's more like assumption. It's somehow connected with assumption.
Okay.
When we obtain, how to say, a Colliger model or Rosenard-Snyder model from the.
Oh wow! This is the way how you obtain Rosenard's model from starting from your
Yes.
representation.
And I remember that in Colliger model, for example, in the case, if we get it from Poisson reduction, we also have this choice of rank 1 matrices, and there we have well,
You might fix it. It is necessary to have rank 1 matrix, but it's not necessary to use these exactly raw vectors. So you may choose it in different ways. It's just a question of gauge choice.
That is what I'm speaking about. The only condition you should have first rank matrix, and how you choose them, it's your privacy.
Okay, but here, for example, this is an assumption. It's clearly assumption because I don't know how why it's natural or something. Well, it's natural because I obtain the final result is the way.
Again, I have impression that you can play with Z and Y. Why? Of course, this is particular choice, but you can say, okay, I want to consider this particular choice. Why not?
Yes. So
this is just a convenient and conventional choice.
Yes. Why not?
I mean, could I obtain something else if I choose a more general case?
Of course. You can obtain something else, but you want to obtain something what you want to obtain, and for doing this, you choose some specification of Z, Y, and W.
Yeah. I agree that this is a legitimate way to obtain Rosenau-Snyder system from KP, but this are a special case of this dynamics of how to say it, eigenvalues of matrix X T, which I have written here. This one. Yes, but this one is if I we have shown that if x instead of this xt will have x, for example, or maybe q, where the q are exponent of initial coordinates, and instead of y and z, I obtain the lax matrix with maybe some coefficients in initial and how to say initial moment of time with indices 0. That this will be the solution in this case. For example, it's clear that this way I didn't obtain something like two eigenvalues I, for example. And I think maybe if I have these eigenvalues of matrix X, for example, are equal, then this somehow I couldn't choose Z in the way that all coefficients of W are non-zero, and in this case, some coefficient should be like zero coefficient. Maybe, I don't know. I have such feelings.
Okay, thank you.
Okay. Спасибо.
That's all I wanted to say.
Спасибо.
Запись можно включать. А у нас